Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another exciting topic. Today we are talking about acceleration. So we're officially done very much with distance and displacement. Of course, we're going to always revisit those topics as we do some questions, but today we're talking about acceleration, and we're going to be talking about graphical representation of acceleration as well. So we're going to learn about what instantaneous velocity means and how to analyze acceleration. Let's have a go. Right, so what is acceleration to begin with? Acceleration is the rate at which an object's velocity changes over time. It shows how quickly something speeds up or slows down or changes direction. So those are the three conditions under which acceleration is taking place. So if something is speeding up, that means it's changing speed or changing velocity from, say for example, 5 to 10, that is acceleration. What if it's changing from 10 to 5? That is also a form of acceleration, which we call deceleration. Okay, so deceleration is actually a form of acceleration itself. What if something is moving at constant speed, but it's moving in a direction where it changes direction? Say for example, the moon around the Earth. Okay, if the moon is rotating around the Earth, okay, then what's going to happen is the moon more or less is moving at constant speed. But because it's changing directions as it's moving in a circle, sometimes it's facing this way, sometimes facing this way, sometimes it's facing that way, sometimes it's facing that way. Whichever direction it's facing is going to change as it moves around the circle. And of course, since it's doing that, it's accelerating. Okay, so how is it accelerating? Well, I'm going to explain a little bit about that. You see, there's a formula in physics that we call the second law of motion. Newton's laws of motion, there are three of them, four if you consider the law of gravitation, which I do, but let's go with three laws of motion for Newton. The second one is force equals mass times acceleration. Many of you will be familiar with this. So what does this mean? It means there is no force unless there is acceleration. Mass is a constant, so we don't have to worry about it. But if there is acceleration, there is mass, and if there is high acceleration, there is if there is high acceleration, there is high force, and if there is high force, there is high acceleration. So acceleration and force are related, which is why if you're sitting in your seat on the plane just before taking off, you experience that acceleration and you experience the force as you go back in your seat, right? The plane is taking off. Now what happens when the plane is cruising? When the plane is cruising, you don't feel anything. You can stand up, you can go to sleep, you can pray, you can do whatever you want. Why? Because there is no acceleration, there is no change in speed, there's no change in direction, and therefore you can sleep. There's no forces. Now what happens if the plane slows down suddenly? Let's say the captain is on the ground and he suddenly pushes the brakes, what's called taxiing. Now what can happen is it can actually cause you to move forward. Why is that? Because suddenly there is a force. So force and acceleration are related to each other. And let's say, for example, you're sitting in your car, driving in your car with your father, and your father suddenly goes around the roundabout. Okay, if you're sleeping, you'll wake up. You'll recognize that you're going around a roundabout. Why is that? Because there is a force on your body. So force and acceleration are related to each other. But we'll come back to visit force and acceleration later on. You don't have to know that now. The rate at which velocity changes. Well, hopefully by now, I want you to pause the video and I want you to answer this. Hopefully by now, all of you know the rate at which velocity changes is known as acceleration, right? Speed is distance over time. Constant speed means it is not changing. It is speed over time that is uniform. And average speed is total distance over total time. Okay, so that's what that means. But we'll come back to visit those a little later. Okay, so let's talk about a few key points when we're talking about acceleration, especially when we're talking about velocity time graphs. A flat line in a velocity time graph means there's zero acceleration. The object is moving with constant velocity. Let's see what this actually means. Okay, so if we look at this graph over here, where's the flat line? The flat line is over here. And as you can see, the flat line indicates constant velocity. Why does it indicate constant velocity? The first thing I want you to keep in mind, my dear students, is this. When you're looking at this graph, the velocity is shown over here. That's it. That's the velocity. So whatever this is pointing to, let's say it's pointing to 50 kilometers per hour, then that is the velocity. You don't have to work out the gradient. The gradient on a velocity time graph equals acceleration. Let me repeat that one more time. The first thing you do when you tackle one of these problems, when you look at a graph like this, is you look at the axis. You look at what the label says. It says velocity. It doesn't say distance. It doesn't say position. It says velocity. This is velocity. This is time. Now we all know in a position time, position, okay, I'm going to just draw X for position, and X, position, and time, which is in seconds. In a position time, the gradient represents, think about it, position time, okay, or distance time, same. The gradient represents speed, okay? And how do I know that? Well, this is meters, this is seconds, meters per second. Rise over run, right? It's y2 minus y1 over x2 minus x1, rise over run. So it's going to be meters in this case, and it's going to be per second here. Meters per second, what is that? Meters per second is speed. So the gradient for this represents speed. What about the gradient over here? What does that represent? Well, let's have a look. Over here, I've got velocity, which, meters per second. That's the conventional SI unit for velocity or speed, meters per second. And of course, we've got time, which is measured in seconds. So what's going to be the gradient in this instance? It's going to be rise over run, once again, rise over run. And it's going to be meters per second per second. Meters per second per second. Or meters per second squared, which is acceleration. So the gradient or the slope on a velocity time graph or a speed time graph represents acceleration. The gradient or the slope on a velocity time graph or speed time graph represents acceleration. And a straight line represents zero acceleration because there is no rise over run. Okay, that's a straight line. It's basically just constant velocity. The slope represents the magnitude of the acceleration. So if it's steep like this, the acceleration is quite significant. But if you look at this one here, that's even steeper. So that's even a more significant acceleration. Okay, so what is happening here then? Here is happening acceleration, and here we have deceleration, which is a form of acceleration in itself. It is decreasing the velocity. How do I know it's decreasing the velocity? Look here. What is the velocity? 50. What is the velocity here? 0. So the velocity has decreased, and therefore we say it's deceleration. So we've covered this point, we've covered this point, and we've covered this point. A steep slope represents large acceleration. We've also covered that point. A negative gradient shows decreasing velocity. And we've also covered this point. Right. So a negative gradient shows decreasing velocity until we get to 0. Can we go past 0? Yes, we can. What happens past 0? Now we're going in the opposite direction. Because remember, velocity has a direction. Okay? So if we have a graph that looks like this, and we go up, we go across, and we go down, then what happens is we've increased our velocity, constant velocity over here, and then decreased our velocity to 0. What if I keep going? What does that mean? If I keep going, it means I'm now increasing my velocity in the reverse direction. That's what that means. Okay? If I keep going in the negative velocity, I'm now increasing my velocity in the negative direction. It's like a car going in reverse. A car that goes, I was going forward, and then I went at constant velocity for a while on the highway, and then I came towards a traffic stop or a traffic light, and so I started slowing down until I got to 0. And then I kept going now in the reverse direction. So I slowed down until I got to 0, and then I started reversing back and speeding up. And that's what that means. Okay? Let's keep going. The difference between uniform and non-uniform motion. Uniform motion means an object moves at constant speed in a straight line without changing direction or speed. Basically, the speed is constantly is the same, or the change is the same. Non-uniform motion means an object's speed or direction changes over time, slows down, or speeds up, or moves in curves, and so on. So here we have an example of what uniform motion looks like. As you can see, it's constant and it's moving in a uniform manner. Over here, the pendulum is slowing down, speeding up, slowing down, speeding up. That is what we call non-uniform motion. The difference between uniform and non-uniform motion, once again, I want to show you on a graph. So this is an example of uniform motion. As you can see, it is uniform acceleration. How do I know that? Look at the gradient here, the rise over the run. It's exactly the same as here. It's exactly the same as here. So what does that mean? It means it is not changing. The acceleration is not changing. The acceleration here equals the acceleration here, which equals the acceleration here. The acceleration is the same all the way through. We call that uniform acceleration, or it's uniform speeding up. It's not changing. What about here? Here's a different scenario. How come? Look over here. The acceleration over here, to begin with, equals rise over run. What's the rise? 20. Of course, it's meters per second. What's the run? 1 second. So what is that going to equal to? Acceleration equals change in velocity over time. Change in velocity over time. So that's going to equal 20 minus 0 over 1. Or 20 meters per second squared. So over here, it's 20 meters per second squared. What about, I'm just going to take a few sections here. What about this section here? I want you to think about it for a second before I do it. Okay, so I'm going to do it now. Is there a rise? There is no rise. Rise is 0. Okay, there is no y component. So it's going to be 0 over 1. 0 over anything is 0. So here the acceleration is 0. And here it's variable. How do I know the acceleration at this point? I take the tangent. Okay, so I draw a tangent that is perpendicular to this point here. And then I measure the rise over the run, and then I can work out the acceleration. And I can see from this tangent and this tangent that the acceleration is changing. And how is it changing? It's increasing. So whatever the acceleration is, it suddenly increases. Okay? Good. What about instantaneous velocity? So I've just kind of covered that at the moment. What is instantaneous velocity? It's the velocity at a certain point in time. So if you look at your speedometer in the car, okay, and I know many of you drive, mashallah, okay, the speedometer indicates your current instantaneous speed, okay, your current speed. It's not your average speed, it's not your normal speed, it's not your sectional speed, it's not your velocity, it is your instantaneous speed at this moment, or instantaneous velocity. I would say instantaneous speed because it doesn't really give you a direction per se. It just gives you a magnitude. So in this case, even though it says instantaneous velocity, I would argue that it's not velocity it gives you, it's instantaneous speed, because it's just a magnitude. Okay, and even if you're going in reverse, it tells you a magnitude. So it gives you your instantaneous speed at that moment. Now, how do we work out instantaneous speed? Well, what I'm going to do is I'll see if I can do this. Can I get a blank screen? No, I don't think I can get a blank screen. So I'm just going to do it over here. Right. I'm going to draw some graphs. 1, 2, 3, 4. This point is 5. And this point is 2. So 2 seconds and 5 meters per second over here. The speed, the velocity. Over here, this point is 5 meters per second as well. They're all the same, and this is 2 seconds. Now, why am I doing this will become apparent very, very soon. Now we have got 5 meters per second again. And here it's 2 seconds. And this time I've got something like this. Okay, so I'm interested in this point here. Right here, 2 seconds. Right here, 2 seconds. Right here, 2 seconds. Right here, 2 seconds. What is the instantaneous velocity for all of these? The instantaneous velocity for all of these graphs is the same, 5 meters per second. Why? Because at this point, it points to 5. It points to 5. It points to 5. They all point to 5. But wait a minute. They're all different graphs. What's different about them? What's different about them is the acceleration. The velocity is the same. The instantaneous velocity is exactly the same. As you can see, it all points to 5. But what about the acceleration? Acceleration is the gradient. Don't forget, acceleration is the gradient. So let's have a look. Over here, the gradient is nearly 0. So there is no acceleration. And remember, acceleration is per meters per second squared. Over here, the acceleration is very steep. Look at it. So we can say maybe it's, I don't know, if we take that, let's say about 4 or 5 meters per second squared. Over here, it's nearly consistent. It's very constant. Okay, so it's about 2.5 meters per second squared. Okay. And over here, it's negative. Over here, I would say it's about, I don't know, negative 2.5 meters per second squared. So even though the instantaneous velocity is exactly the same, the acceleration is different. Okay, so just be careful with that point. All right, hopefully that made sense. Let's look at this question over here. This is the total distance divided by the total time for a trip. Total distance divided by total time. Okay, total distance divided by total time. Let's talk about going to Riyadh in Saudi Arabia. Now we're over here in Kuwait at the moment. I don't know how far Riyadh is. I think it's about maybe 800 kilometers away. Let's assume it is. Okay, so over here in Kuwait, Riyadh's over here. Now I'm gonna go around the place until eventually I get to Riyadh. Now during that journey, there will be times when I'm speeding up, times when I'm slowing down, times when I'm completely stopped, taking a break, times when I'm going at constant speed. So what is my overall average speed for the journey? Well, my overall average speed is going to be total distance divided by total time. Total distance divided by total time. And that's going to give me my average speed. What about average velocity? Average velocity is going to be the shortest distance, or my displacement, which is from point A to point B. So this is the displacement now in the dotted line. Displacement over time is going to give me my velocity, my average velocity. But it's going to be the total displacement, okay? So that's how to work out the average velocity, or the average speed. Shall we say the average speed? Average speed is going to be total distance divided by total time it took. So let's say, for example, 800 kilometers and it took 10 hours. Then it's going to be approximately 800 kilometers, about 80 kilometers an hour, something like that. So either way, this is the average speed. Let's move on. This is the actual speed of a moving object at any moment, at any instant. Now this is what the speedometer gives us. What is this? It is going to be the instantaneous speed. Okay? Curved segments on a position time graph mean the object speed is changing. Okay? Pay attention to the gradient of the slope. Yeah, that is true. The object speed is changing. Now what's happening here? What's happening here is we've got the curve is changing. How is it changing? It's increasing. It's becoming sharper. So therefore there is an acceleration happening. And it's going from a negative position to a positive position. So it's going forward. So it's going forward and speeding up. Remember, this is important. This tells us what's happening. We're starting over here, we're starting forward in the positive, and we're going to the negative. So we're going backwards. Once again, the gradient is increasing, but we're going in the negative. So this is negative acceleration or negative speeding up. That's all that is. because the gradient is increasing, but it's going in the negative direction. What about here? We're going from negative to positive, so that's already going forward. And what's happening is we are slowing down. Why? Because the gradient is becoming flatter, so we're slowing down, but in the positive direction. And what about this point here? In this point here, we are once again slowing down. Oops. We are once again slowing down, but we are going from positive to negative. So we're going in the negative direction, but we are slowing down. Decelerating. Decelerating means slowing down. Negative acceleration is not slowing down. Negative acceleration means you're speeding up in the negative direction. Okay, so for example, a car that's speeding up in reverse, that's negative acceleration. Slowing down is a car, it could be going forward and slowing down towards a traffic light. Okay, so that's deceleration. What is happening in this graph over here? First of all, remember what I told you. You look at this part here first. Is it distance time? Is it position time? Is it speed time? Is it velocity time? It's very important. It's velocity time. So remember what we said. The area under the graph is going to represent displacement. The area under a velocity time graph represents displacement. The area under a speed time graph represents distance. The area under a speed time graph represents distance. The slope of a speed time graph represents acceleration. I think Saif is yelling out the answer right now. Acceleration. The slope of a velocity time graph represents acceleration as well. Over here we've got constant acceleration or uniform acceleration. Here we've got increasing acceleration. Why? Because the gradient is changing and it's becoming a lot steeper. What's happening over here? We've got constant speed. Okay, or constant velocity. They both have the same magnitude. Okay, and what is happening in the last portion is that the velocity was over here, let's say for example 50, and then it went down to 0. So we have deceleration, or in physics you might hear a new word now, retardation. Retardation means slowing down. So constant deceleration or retardation. Let's have a look at these examples over here. Velocity time, we're dealing with velocity, we're dealing with time. The first example, the velocity is not changing. Time is going forward, but the velocity is not changing. This is an example of constant speed or constant velocity. Next one. What's happening? The velocity is increasing. Over here, I have one velocity. Over here, I have the velocity and it's increasing. So therefore, this is uniform increase or uniform speeding up or uniform acceleration. What's happening over here is that the gradient is increasing. And so this is what we call, what is this? Non-uniform acceleration. So it's increasing, non-uniform, positive acceleration if you like. But it's increasing at a non-uniform rate. It's increasing the further we go. And over here we've got retardation. But why? Because it's slowing down. And then it's speeding up again. So if you want it to be specific, if you want it to be pedantic, you can say it's slowing down and then it's got uniform deceleration, and then it has it's first of all, it's not slowing down. It is yes, it is. It's slowing down because the velocity is over here, and then it decreases in a non-uniform manner, and then decelerates at a uniform manner over here, and then finally it slows down further at a non-uniform manner. So non-uniform retardation is an easy way of saying that. Non-uniform retardation. The point is, it was here and then it ended up here. So the velocity is decreasing. Okay, we've got some questions to answer. Describe the journey in as much detail as possible. Give values for speeds, acceleration, and distance traveled. From 0 to 20 seconds, the vehicle is at what? Here's 0. Here's 20 seconds. Now this is the time when you actually pause the video and do it yourself, please. 0 to 20 seconds, what is the vehicle doing? It's going at constant speed or constant velocity. Why is that? It's 12. 12 here, 12 here, 12 here. It's not changing. 12, 12, 12 all the way, so it is constant and uniform. Constant speed of 12 meters per second. If I remove my face, but it's just going to make things more complicated. In this time, it covers a distance of what? Now, how do I work out the distance? You should all know this by now. It is the area under the graph. So in this time, it's going to cover a distance of, this is the base. Oh, sorry. Base, and this is the height. So it's going to be base times height, or 20 multiplied by 12, 240 meters. Well done, Abdulaziz, because you answered it today. 240 meters for that one. Okay. Next one. From 20 to 30 seconds, what is happening? The car is what at 30 seconds? Let's have a look. The car is completely stationary at 30 seconds. It stopped at 30 seconds. So it's decelerating. It's decelerating, and it finally stops at 30 seconds. Decelerates or slows down to a stop at 30 seconds. The deceleration is equal to velocity change over time. So what is they want us to calculate the gradient, because remember, acceleration equals the gradient of a velocity time graph. So the deceleration is the same. So it's going to be 12, which is the height, the rise, over the run, which is 10. 12 over 10 equals negative 1.2. Okay, but how do I calculate it? Let me show you the calculations. Of course, by now you should know that acceleration equals v2 or vf, final velocity, minus initial velocity, vi, initial velocity, over change in time, t2 minus t1. Where have you seen this? You've seen this in maths. Okay? The gradient equals y2 minus y1 over x2 minus x1. Maths and physics are practically the same. So we've got v2, which is over here. That's v2. Why? v2 is 0. Okay, so that's v2. And that's v1. So 0 minus 12 over 30 minus 20, which equals negative 12 over 10, which equals negative 1.2 meters per second squared. That's the answer. That's how you do it. Next, the distance traveled while decelerating equals the area of the triangle. Of course, it's the area under the graph, whatever that area is. If it's a triangle, then it's half base times height. If it's a rectangle, it's base times height. If it's a semicircle, it's half pi squared, and so on. Whatever you have, you use. So, the distance traveled while decelerating equals the area of the triangle, which equals half base times height. So it's going to be half times 10, because this the base equals 10. Multiplied by the height, which is 12. So it equals 60 meters. Total distance traveled. Now they want the total distance traveled. Now the total distance traveled is going to equal both sides. I have 60 over here, and I have 240 over here, which I worked out from before. So it's going to be 300. 300. The mean speed, and mean here doesn't mean nasty. Mean means average. The average speed of the vehicle over the whole journey is the total distance divided by the total time. Do we have the total distance? Yes, we have it over here. Do we have the total time? Yes, we also have it over here. So it's going to be 300 meters divided by 30 seconds, which equals 10 meters per second. Okay, I hope that wasn't too hard. Good stuff. Let's move on. A car travels between two sets of traffic lights. The diagram represents the velocity time graph for the car. Does this make sense? Let's see. The car was speeding up, slows down, then moves at constant velocity, then slows down right to a stop when it gets to the second traffic light. Yeah, makes sense. Use the graph to find the velocity of the car after 15 seconds. What is the velocity of the car after 15 seconds? Let's see. Okay, that was a terrible horizontal line that I just drew, so hopefully you can draw a better one. I don't know, about 11 point something. I'm just going to say 11.5 meters per second. Between 11 and 12 meters per second, that's for sure. Calculate an estimate for the acceleration of the car in meters per second squared after 10 seconds. After 10 seconds. They want an estimate. So here's the 10 seconds, and they want an estimate of the acceleration. How do I calculate the acceleration? Of course, in order to calculate the acceleration, I need the gradient. So I need to draw a tangent here. And then I can take the rise over the run. Does the tangent have to be big? No, absolutely not. I can draw a short one. And so I can approximate. Okay, I'm not going to do it for real, but I think it's about maybe 3 over 5. 3 meters per second over 5 seconds, which is approximately 0.6 meters per second squared. Okay, I'm just eyeing it. I'm not even sure if that's correct, but that's how you do it. Below is a sketch of a speed time graph of a cyclist moving on a straight road over 7-second period. That's velocity, and that's time in seconds. So it's velocity time, so therefore the gradient means acceleration. The acceleration for the first 3 seconds is what? They want the gradient of this line. How do I do it? Remember, it's y over x, rise over run. But I'm only interested in this rise. Don't go all the way down. Why not? Because it's not this. It's only this. So it's rise over run, which is going to be 3 on this side and 3 on this side, 3 over 3, which is 1 meters per second squared. Okay? And in the quiz, you have to say acceleration, because it's worth 2 marks, right? It's worth 2 marks. So you have acceleration equals change in velocity over time, or change in time. It doesn't matter. You can say change in velocity over time. You can say Vf minus Vi over t. You can say V2 over minus V1 over T2 minus T1. They are all correct, okay? There is no one formula that's better than the rest. It's all the same, okay? So whatever you write, as long as it's correct, the examiner should mark it correct. The distance covered by the cyclist over 7 seconds is what? The distance covered by the cyclist over 7 seconds is going to be the area under the graph. So I'm going to cut this graph into 3 portions. Y3 just makes it easier. Area A, area B, area C. What's A? A is half base times height. I'm going to do it the long way. There is a shorter way of doing it, but I'll just do it the long way. So that's 3 times 3, which equals 3 times a half, which equals 4.5 meters. What about B? B equals base times height, which equals 3 times 2, which equals 6 meters. And C, remember it's not 7, it's 4. Okay? 7 minus 3 is 4. So once again, base times height, which equals 4 multiplied by 5, which equals 20 meters. 1, 2, 3. So the total area is going to be 30.5 meters. That's the distance. The total distance is going to be 30.5 meters. Moving on. Extra practice. Are you ready? I would like you to pause the video and work on these before I reveal the answer. Good luck. Okay, don't pause the video now. Pause the video once I show you the question. And then work on it, and then I will reveal the answer. Are you ready? 3, 2, 1, let's go. Question 1. Pause the video. Try and work on it yourself, and then unpause the video and reveal the answer. So name, Mr. A. Graph below shows the journey of 2 cars. There's car 1, car A, and there's car B. Which car is traveling at a constant velocity? So here's the velocity over here. Which one's constant velocity? Of course, it's going to be car B. It's not changing. 10, 10, 10, 10. It's not changing. So the car moving at constant velocity is car B. You don't have to write car B. You can just write B. When are both cars traveling at the same velocity? They're traveling at the same velocity the moment the lines intersect. So where do they intersect? Right here. So that's going to be the point at 20 seconds. They're both intersecting, they're both traveling at the same velocity, which by the way is 10 meters per second. But didn't ask you what the velocity was. Remember, read the question carefully. It says when, so it wants the time, not the velocity. So 20 seconds, and they're traveling at 10 meters per second. Which car had the highest displacement at the end of the journey? Right, so now we have to do some calculations. Highest displacement. First of all, let me figure out what's the end of the journey. The end of the journey is this point here, 50. And then for car B, it's going to be the area under the graph, right? Because it's velocity time, so the displacement is going to be 50 times 10. For car B, it's going to be 50, which is base times height, times 10. Base times height, 50 times 10, which equals 500 meters. That's the displacement. What about car A? Car A, the journey is shaped like a triangle. Oh, that's just too excessive. Half base times height means it's going to be half times 50 multiplied by 25, which equals 25 by 25, which is 625 meters. But that's not the answer. Remember, read the question carefully. The question says, which car had the highest displacement? You can't just work it out and expect the examiner to pick the answer. Okay, clearly it's A, but that's not an answer. So you have to say, you have to answer the question, car A had the highest displacement. Now there's one more thing I would like to talk about. Displacement is a vector, so it has a direction. So what is the direction? Well, we don't know whether it's north, east, west, whatever. So what you can do is say it's positive 625 and it's positive 500. Because that's all we know is that it's positive. So the positive in this case becomes the direction. Next, the graph below shows information about part of a skateboarder's journey. Work out an estimate for the acceleration in meters per second squared of the skateboarder at 6 seconds. Where's 6 seconds? This is speed and this is time. So at 6 seconds, it's over here. How do I work out the acceleration? Remember, the acceleration is going to equal the tangent or the gradient, the slope, whatever you want. So they're asking me for an approximate value. Oh, this is horrible to write on glass. Anyway, at 6 seconds, that's it. That's the best I can come up with. So remember, it's y over x, or rise over run, or v2 minus v1 over t2 minus t1. So my v2 is approximately 5.5. Remember, v2 minus v1 over t2 minus t1. 5.5 minus 4.5. See? Approximately 4.5, and that's approximately 5.5. Excuse me. And of course, the time is 2 seconds. 7 minus 5. So it's going to be 1, meters per second. No, meters per second over 2 seconds, or half meters per second squared, or you can write it as a decimal if you prefer, half meters per second squared. That's the answer. It's a terrible tick. Here you go. 3 ticks, because 3 marks. So when we're looking at 3 marks, I expect 1 mark for the formula, 1 mark for the workout, and 1 mark for the answer. But you'll also lose half a mark for the incorrect units. So make sure you have the correct units, please. And finally, the graph below shows the motion of a motorcycle. Answer the following questions using the graph. After what time has the motorcycle stopped? Remember, this is not distance time or displacement time or position time. This is velocity time. So the flat line, this flat line over here, does not represent a stopped motorbike. It represents a motorbike that's traveling at constant velocity. The motorbike stops when the velocity is 0, which is over here. So when did the motorbike stop? The motorbike stopped after 0.7 hours or 42 minutes. Doesn't matter what you write. What is the velocity of the bike at 0.4? You simply have to do this. What is the velocity of the bike? 60 kilometers per hour. Please don't forget your units. Between what times is the bike decelerating? Decelerating means it's slowing down. Here it was 60 and here it's 0. It's slowing down between 0.6 and 0.7 hours. When is the bike traveling at constant velocity? We've answered this one already. 0.3 to 0.6 hours. What is the acceleration between 0 and 0.3? Use the formula. Change in velocity over time. We already did this. You guys are geniuses at this already. Change in velocity over change in time. That's also acceptable, change in time or whatever you want. So it's going to be, what is it? 0 to 0.3. So they want this section. Okay? So the final velocity is 60. The initial velocity is 0 over here. And the final velocity is 60. The time is 0.3 minus 0. 60 divided by 0.3, which last time I checked is 180. No, it's 200. Whoops. It's not 0.33, it's 0.3. So 100, not 180, 200 kilometers. Oof. 200 kilometers per hour squared. That's how you do that one. Okay, that is crazy acceleration. Yep, 60 divided by 0.3. Yes, it is 200 kilometers per hour squared. The biker was going very fast. Anyway, what if I wanted to change it to meters per second? Can I do that? Yeah, we can do that. We can do that. So let's write the answer. 200 kilometers per hour squared. What if I want to change it to meters per second? Well, let's see. V2 is 60 kilometers per hour, which equals 60,000 per 3,600 seconds, which equals 16.7 meters per second. Okay, and of course the time is going to be 0.3 hours, which multiplied by 60 is equal to 18 minutes multiplied by 60 is equal to that many seconds. So it's going to equal 16.66666 divided by this many seconds, or 0.015 meters per second squared. Very interesting. Okay, and that is all from me. Thank you so much. I hope you enjoyed that. You don't have to change from kilometers per hour to meters per second unless the question explicitly asks you to. That is all. Take care. All the best. Let's see, can I write on this? Keep. Okay. Bye-bye.